I will today first give you some remarks about UCL for the ones of you that don't know it that well. And then I will, my talk will be a little bit more technical. But to start it, welcome to UCL. So UCL is also named the home of the brave thinkers. It was founded by 1826 by Jeremy Bentham. Jeremy Bentham was a philosopher, an educator, but also a medic. And UCL was the first non-religious university in the UK. So it was the first university in England to welcome students of any religions or social background. It was also, very importantly, the first university to welcome women to a university education, and has been, relatively recently, the first university in England to have a fully open access university press. We try to continue to challenge inequality, break boundaries, and confront humanity's biggest issues today. Now, a few UCL in numbers, but also a little comparison with Tsinghua University. So we were founded about a little less than 100 years apart, but we have a very similar number of students, although for us many more are foreign students. And there is a slightly different ratio in female to male students, according to the statistics. But very interestingly, we are very similar in the education point of view. We have a similar ratio of teachers to students. We like to teach to small number of students, and we like to teach very personally. And also that is reflected in the international rankings. Quite interestingly, depending on the rankings that you look at, Tsinghua might be better than UCL, or UCL might be better than Tsinghua, but we are more or less in the same positions. So with that, a little bit more news about UCL. So this is our Bloomsbury campus in the heart of London, very close to the British Museum, for the ones of you that have been to London. And we have also a second campus, which is in the Olympic Park. So following the Olympic in 2012, this area of London was regenerated, and as a result of it, we also established some UCL departments and laboratory there. In particularly, my laboratory sits in this building here with the big red arrow, which is called UCL at Here East, and I will show you a little bit more what we have in there. So, but let's come to the Faculty of Engineering, which has many remarkable similarity to Tsinghua Department of Civil Engineering. So the Faculty of Engineering Science is over 190 years old, and because the first professor that was appointed in engineering in UCL was a professor of civil engineering, and that was to improve the quality of the urban conditions, especially to improve the roads in the city and to improve the sewage system for public health. It now has 10 departments, 26 undergraduate programs, 112 postgraduate programs, and more than 120 different nationalities. So quite an international outlook. And this is the list of the departments that we have in the faculty. And as you can see, along the more traditional civil, electric and mechanical engineering, we have, of course, computer science, but also medical physics and biomedical engineering, and even security and crime science, along with the School of Management. Going into civil and geomatic engineering, we have a diverse academic group of about 70 staff, and we cover from structure and infrastructure design, as is my case, to transport, circular economy, disaster risk reductions, and also the more traditional hydraulic, geotechnics, and so on. We have a wide network of industry and academic connection. I had the pleasure from the past 5 years to be able to set up the strength laboratory, the structural and environmental integrated testing at here East. This is quite an innovative facility because for the first time we bring together environmental conditioning and testing with mechanical testing, as you can see in the green frame. And if you open these two frames, what you will see is something like this, where we are able to have two environmental chambers that can control both outdoor and indoor hygrothermal conditions, but also produce wind-driven rain, plus also accommodate specimens up to 4 meters and can be subjected to up to 300 kilonewton of horizontal and vertical loading. Very small compared to your new facilities here, but still, it's for London, where there was no facility whatsoever. It's quite large structures, which allow us to test to full-scale structural elements. Another element, we are also very concerned with the sustainability and sustainable structural engineering. So next to the chamber, we also have this rig, which is very large. It's 9 meter long by 4 meter wide, and has 4 servo-hydraulic actuators, which can transfer up to 1,200 kilonewton, doing high cycle fatigues. And we can, for several tens of millions of cycles, to test new sustainable composite structural system with low carbon footprint. So what you see there, for instance, is a composite of steel and cement-free concrete deck. But also we test stone and timber composites, and this is the work of my colleague, Professor Wendell Sebastian. Out of the activity and the research that we do in this laboratory, we have set up an MSc in sustainable structural engineering. This is the first year that the MSc is running, so for the ones of you that intend to come and study more structural engineering in the UK, please have a look at it. This course will provide you with the skills required to lead the design of safer, more resilient, and smarter building. The teaching is industry-led and design-based, and you will explore structural engineering within the climate emergency context, the net zero issues, well aligned with the UN Sustainable Development Goals. The type of teaching that we do within the civil engineering department is a bit different than many more traditional civil engineering courses. For instance, an undergraduate course that I contribute to develop with colleagues from the architectural and environmental engineering faculty is the MEng in engineering and architectural design. This is the first course of this type as undergraduate in the UK. We have the 3 disciplines in 1 degree, and it lasts 4 years. It's an integrated design programs which combine architectural knowledge, creativity, and vision with evidence-based structural and environmental engineering. And what is very important is that the graduate of this course are then able to become either architects, civil or structural engineer, or building services engineer, or what is currently very topical in the industry, at least in Europe, facade engineering, i.e. the integrated way of making building breathe and stand at the same time. So this is an overview a little bit of what we do at UCL. I will now introduce the UNESCO chair, which both Professor Dongping and Professor Qingchen Lu already referred to. So the UNESCO Chair was initiated in 2021. It's called UNESCO Chair on Disaster Risk Reduction and Resilience Engineering, and try to develop effective methods to assess and mitigate the risk of damage by natural hazards to existing and new school buildings. In this way, the Chair contributes to improve the equity of access to safe learning environment for children in vulnerable communities by ensuring continuity of the education services to reduce lost school days and lost lives at school. This is a picture of the team, which has changed in the past 4 years, and Dr. Zheishang Li, a graduate from Tsinghua, both undergraduate, master's, and PhD at Tsinghua, is very welcome to London and has joined us now for more than 1 year and has contributed quite importantly to the activity of the Chair in this past academic year. So the Chair has 4 objectives, and I will very quickly explain them. And the idea is that we promote climate and hazard resilience school and their critical infrastructures. So the first objective is to develop a multi-hazard holistic resilience engineering framework. This is, some of you might know the Global Alliance for Disaster Risk Reduction and Resilience in the Education Sector. This organization brings together, for instance, the UN, the UNESCO, the World Bank, but also the Red Cross and so on, and other global organization, and has issued the Comprehensive School Safety Framework, which along the Sendai frameworks try to bring more safety and security in the education sector. So the first pillar, which is of particular relevance to engineers, is the safer learning facilities. And if we look at the way that we define risk in structural engineering, so considering the hazards, considering the vulnerability, and considering the exposures, then if we can quantify risk, we can then deliver resilience. So that's the framework within which we try to work, and this framework helps us to achieve the sustainable goal number 9, build resilience infrastructures and promote inclusive and sustainable industrialization and foster innovation. The second objective of the Chair is to develop efficient and low-cost school infrastructure data inventory and exposure characterization tools, and we have done this by collaborating quite extensively with colleagues, especially in the Philippines. Again, it's a long-term collaborations since 2017 with a number of different projects. So, and we try to not only characterize and minimize education disruptions, but also build affordable and accessible decision support tools that local community can use to look at what resources they can use locally in order to improve the behavior of their schools. And we have done this collaborating with the Lloyd's Registered Foundation, Xavier University in Cagayan de Oro in the Philippines, and the University of Glasgow. The third objective is to create a culture of resilience engineering with online resources. So, since the inception of the Chair, which is almost at the end of its 4th year, we are 6 months away, we have run 35 webinars in 36 months. In fact, one of the webinars was delivered by Professor Dongping and Professor Nan a few months ago in the first terms. And all these webinars are also available online on our YouTube channel. So people that have not had the opportunity to listen to them live, they can go back and learn from it. And this leads us to our fourth objective, which is sustainable networking through the permanent hub of a community of practice, which we have now developing with more than 3,000 people from many different, almost 100 different countries in that attend those webinars and continuously comments and so on. The webinars always, we try to make them once a month within lunchtime in UK time. It's evening in the east and early morning in the west, so that everybody possibly can link in, and you are all welcome to attend. They are open to everybody, and they are open for discussion afterwards. And this, in the idea of this community of practice, the collaboration between UCL and Tsinghua is very important. So in just before Christmas, our president visited, and our vice provost visited Tsinghua, and they, together with Professor Dongping, they signed a memorandum of understanding between our two departments of civil engineering. As I said earlier, UCL offered an honorary professor to Professor Dongping Fang, and now very honored to also receive the distinguished visiting professorships. So this gives a little bit of an overview of our relationship and what we do at UCL. Thank you very much for listening. I don't know if there are questions at this point, or I will go to the next presentation.
I think you just go ahead.
Okay. Oops. So my lectures today will be about improving school infrastructure resilience to earthquakes and flooding. And this work is developed in collaboration with the research associates on the UNESCO chair, Dr. Rafael Fernandez, Dr. Zheishang Li, and Dr. Asana Paramal Batteri. A very brief list of contents of the lecture. So we'll look first at the global context. We then look at what is the global problem, and then we offer some what we call the disaster risk reduction and resilience engineering analysis methods. We apply to our case studies, and then there will be some conclusions. So let's start from the Sendai framework targets. So the Sendai frameworks, which was initiated in 2015, and in theory it should be accomplished in the next 5 years, although we all know that we are a bit late with meeting those targets, has 7 main targets, 4 that aims at reducing risk, and 3 that focus on enhancing resilience, as we can see from these arrows. Of these targets, today, I will briefly refer to targets D and targets E that are particularly relevant to the issues of reduction, resilience, risk reduction and resilience in the education sector. So the targets E talks about the number of countries that adopt and implement national disaster risk reduction strategy in line with the Sendai framework for disaster risk reductions. And in the second target is the percentage of local government that can adopt and implement local disaster risk reduction strategies in line with national strategies. So first the national strategies, then the local strategies, using the information that should be provided at the appropriate level of government below the national level with responsibility for disaster risk reduction. And then the D target is about reducing the number of destroyed or damaged educational facilities attributed to disaster. So you see, it's quite, the Sendai framework has quite specific information about the reduction of damages into school infrastructures. And by doing this, we again can fulfill all these, mainly the first 3 sustainable goals, 9, 11, and 13, but also by fulfilling those goals, we also reduce poverty, we improve quality of education. If the infrastructure is better, then we will have better clean water and sanitation within the schools, for instance, better affordable and clean energy, hence people with better education will have better work and economic growth, and this will then lead to peace, justice, and strong institutions. So the sustainable goals, we always need to think that are strictly connected among them. What do we do with the UNESCO chairs and with the use of advanced technology to assess critical infrastructure? We try to engage with the national level institutions, for instance, in the Dominican Republic, directly with the government through the BERLAC project, or we try to engage with the stakeholders and local authority with projects in the Philippines, for instance. And we address D3 by looking at ways of reducing the number of schools with damage and reducing the number of bridges that are damaged, as we will see in a minute in our procedure. What is the global, besides the Sendai frameworks, I already mentioned the comprehensive school safety framework in the previous speech. And again, I draw your attention to Pillar 1. So let's go a little bit more in details into this. The Pillar 1, it's about safer learning facilities. And in particular, as we can see there, safer and greener facilities that are built according to codes and standards. So it's very important that the nations have those standard codes, that there is construction quality control, that there is assessment and interventions, and also that, so for the existing building, and that water, sanitation, and hygiene are also addressed. And the interaction between the first pillars with the other pillars also provides structural safety education, so people are actually educated to think about structural safety. People are educated to building maintenance and non-structural mitigation, such as fire safety. And by fulfilling these different, let's say, objectives, then we really build the child rights and resilience in the education sector. But in order to do that, we need to look at the existing building stocks in the school education sector. So why is exposure so critical to safer school? If we look at a school, for instance, this one is a school in the Philippines, we can see that there are a large number of different buildings just in one compound. Here there are more than 10 buildings. Each of these buildings is slightly different, might have a different response to an hazard, might behave differently, and therefore can be subjected to different damage and cause a different hazard to the occupants. But on the other end, the school infrastructure is existing and is being used. As I said, each school building might have its own vulnerability, and therefore every school building might need improvement to be safe. We need to quantify this way. So what is it that we should prioritize? Because clearly the resources at any given time will be modest or will be confined, and we will not be able to address the school, the complete safety or renewal of the school infrastructure at once in any country for that matter. So together with the World Bank, we have tried to develop the GLOSSy, which is the Global Library of School Infrastructure. The idea is that worldwide, typically schools have the same function as building from an architectural point of view, and they are built in a very similar manner as a number of classrooms with corridors and then connected. So indeed, we can identify specific taxonomy or specific list of parameters that identify each building from a structural point of view. We can then make a catalog of building types, which will be important not just for one country, but across a large number of countries. Once we identify the building type using structural knowledge, we can identify the vulnerability and fragility data, and then once we have identified the vulnerability and fragility data, we can identify the vulnerability reduction measure and therefore solution, and therefore quantify them in terms also of costs. So, excuse me, we can consider this taxonomy like the DNA of school buildings and school compounds. But schools are not don't exist in isolation. So, for instance, if we look at this city here, we can see that there is a number of schools in the city center. One is further ahead. They are connected by roads. They are connected by bridges. And if there was, for instance, a flooding here, clearly some of the bridges will be affected. There will be a problem for the pupils to go to the school. And if a school is flooded, for instance, how can I move students to other schools? At the same time, I can also see that each of the schools, again, has different layout, different buildings, and a different, therefore, vulnerability. So, what is the disaster risk reduction and resilience engineering analysis framework that we are taught about? So, first of all, we want this framework to be able to work for different hazards. For instance, here we are illustrating seismic and flood hazards, but it can also be windstorm or hurricane and typhoons. Secondly, we start from the current condition of both the school, which sometimes are also used as shelters, and the transportation infrastructure. We can then use Bayesian network and agent-based model, and I will explain in a minute how we do that, in order to determine the school resilience and therefore the education service disruptions. But we can also think of updated conditions and school shelters and transport infrastructures that can come from a set of pre-disaster interventions to improve the resilience of the system. So at each of these iterations, we can think if we can assess all the intervention possibly, yes. Have we identified efficiency cost metric for the set of intervention? Or if not, then let's look at selection of a particular intervention and start this tour again in order to improve the system. So in other words, how we are going to measure the effectiveness of the intervention. We can measure the effectiveness of the intervention in terms of recovery strategies. And if we look at this a little bit more in details, so we have a number of current infrastructure conditions which is affected by an hazard in the region. Now, the hazard is probabilistic in nature, i.e. we don't know where it will hit, when it will hit, with which intensity it will hit, but we can assume certain probabilistic distribution for each of these. In the same way, for what concern the assets, the school or the bridge or the road characteristics, we will have what we call fragility functions, but again, this will be probabilistic in nature. So we can use Bayesian networks, as we will see in a minute, in order to describe the uncertainty around the problem. We are then interested in knowing, after an event, in the current condition, what are the operational capacity state probabilities of each of the assets. And in order to do that, we will need to we will have generic probabilities, but in order to understand how the system works, we will have to perform a number of Monte Carlo simulations, which are events, a number of possible states in which the system will be. And the larger the number of Monte Carlo simulations, the better the way in which we can address the uncertainty. Finally, we can consider different recovery strategies. In this case, we will use, for each of the Monte Carlo simulation, we can use an agent-based model that will go through the recovery for that particular simulation. And once we have arrived at that, again, we will have a large number of solutions. We can then identify the system resilience and the educational service disruption. But we can also bring in retrofitting strategies and then go through the same process and identifies an improved system resilience and a shortened educational service disruption, which would also means that we will, in extreme condition, we will be in a position to save more lives. I will now try to illustrate a little bit more in detail this process, and then we will also look at an application very quickly. So let's look at the Bayesian network first. So the Bayesian network is a probabilistic directed acyclic graph where nodes present variables and edges represent causal dependencies among the variables. The dependencies are quantified by the conditional probability of each node given its parents in the network. So what we are looking at here is that, for instance, given parents node A and B, then the probability of C will depend from the probability of A occurring, but the probability of D, for instance, will depend both from the probability of A and B occurring, and the probability of E will be a function of the probability of D. So let's apply this to a specific school building. I will have hazard intensity that, for simplicity here, we will consider as a non-probabilistic measure. So we will choose a particular scenario, and for that scenario, we will have a certain intensity at the site. Then, for that intensity at the site, through the fragility functions, the school will be in at least 4 different probability of being in a given damage state. Given that probability of being in a physical damage state, then I can consider the functional states of each building, so whether it's intact, partial, or shut down. Given the number of buildings in the school with this different probability of being intact, partial, or shut down, I can then consider what is the state of the school, and that the state of the school will not, the state of operational capacity of the school, i.e. the possibility of delivering lecture, will not depend only on its functional states, but will also depend on what we call the social vulnerability status of the community that is related to that school. So if we look at the local community, we can look at the income profile, at the education profile, and the housing profile, for instance. These are just 3 indicators, but we can use other indicators. Depending on the level of these indicators, we can imagine that the social vulnerability of the community has different heights. For instance, if I have good schools, good education profile, and good income, I will react to a disastrous event in a different way that if I have a poor house, which might be directly affected by that event, and I don't have economic resources to, for instance, access a different shelter. So I will need the school as a place where I need to shelter for a certain amount of time until my home is going to be recovered. Then, if the school is used as that shelter, then very often it cannot deliver lessons. It cannot be used for educational purpose. So by integrating these two elements, then we can have the operational capacity of the schools. And this can be quantified in these terms. So for instance, here we are considering two different scenarios. We are considering different combination of 12 different combination of schools, which I will go a little bit more in detail in the following. Oops. And it will give me different extremes. Similarly, I can do a similar approach for the bridges or for the roads. In this particular analysis, we have considered that bridges will mainly be affected by earthquake and roads will be mainly affected by floods. But that's not, again, it's a simplification and it's not necessarily, it's not a limitation. And this, for instance, is one of the bridges that has been affected by the very recent earthquake in Myanmar, which occurred 3 days ago. I know, Xinjiang, that you have already produced some analysis of it. So let's move on to the Monte Carlo simulations. So the Monte Carlo simulation for this table of probability that you have seen in the previous slides, then we will have, depending on the number of simulation, we will have different states and different combination of the states for each of the, for the system for each of the schools. So this can be summarized in terms of probability distributions here. And the larger, as I said earlier, the larger the number of simulation, the more this distribution of probability complexity will tend to the distribution probability that we have looked at in, for the Bayesian network. Now, in order to understand how the recovery works, for each of these simulations, we will need to run an agent-based model. So if we have 1,000 simulations, then the agent-based model will have to run 1,000 times. And how does the agent-based model work? So the agent-based model works with two different agents. One that strives to retrofit the schools in the most efficient way, and one that strives to retrofit the bridges in the most efficient ways. But as you can see, I think there is a pointer here. Does it work? Maybe not. Can you see it? No. Maybe it's this way. No. It doesn't matter. So as you can see here, the agent for the school needs to wait until the bridge is fixed in order to go and recover the target school, i.e. if the road is broken and it cannot pass, then it cannot proceed. So for each of the school operator and bridge operator, the target is to find the next school by criticality, and by criticality we understand ranking of the schools and the bridges in different terms that we will see in a moment. But also the two agents are forced to interact with each other. i.e. one will need to complete the recovery and wait until that recovery is completed to unlock the next school that can be recovered. Or, in the other direction, the school operator can inform the bridge operator that he needs a particular bridge to be opened in order to recover the school. So he can influence the activity of the bridge operator. So as I mentioned, we do this 1,000 times, and then we have a very wide distribution of the time to recovery in a moderate earthquake or in an extreme earthquake. And then, as you can see, there is quite a dispersion there. But for the purpose of thinking about this, we can then use the median of that dispersion. So in the rest of the analysis, we will use these median curves. So now I'm trying to apply these concepts to the case studies. And for these case studies, we have considered this wonderful place, which is San Pedro de Macorís, a province in the Dominican Republic. And the Dominican Republic is a country in the Caribbean which is affected by both earthquake. It's next to Haiti. You might have heard already of the several earthquakes in 2011 and 2021 that affected Haiti quite strongly. The Dominican Republic also had a strong earthquake in 2011. Has not had recent earthquakes, but it's very earthquake prone. And also has floods and hurricane affecting it. So the idea is to identify the educational interruption that comes from natural events and to optimize alternative for strengthening of the infrastructures evaluated in terms of the benefit cost assessment to support decision making. So as you can see down here, in order to achieve this, one needs to work quite a lot with a number of governmental institutions in order to obtain the fundamental data that is necessary to run similar analysis. So here, just some very simple statistic of this area. This is the distribution of the schools. There is a concentration in the cities, in the San Pedro de Macorís cities in the southern part of the pictures on the left. And you can see that then in the region they are much more dispersed. There are almost 400 schools facilities for about 1,000 buildings and about 100,000 students. And this is the connectivity in the country, in the region. And again, we can see that there is a majority of roads here in the cities, but then when we go outside the cities, there are very few roads, and these roads are also not necessarily very resilient, very strong roads. So some of them are secondary or they are not tarred and so on. They are not highways and bridges. So if we look at it from the point of view of simplifying the network, so for each of the municipalities in the region, we identify a different node, and we identify the distances. Here we just schematically indicated as linear, but of course we take the actual length among them. And you can start seeing the different type of buildings that constitutes the schools. What is interesting is, of course, that in each region, and you will know this by experience also going to school yourself, there is a finite number of school typologies. Yes, so buildings tend to be the same, more or less. And that helps us a lot when we are defining the vulnerability of these buildings, because if we analyze one, and that's where the glossy approach comes in. But there are also a number of bridges that here are indicated in yellow. And these bridges are critical connections between the different nodes. Also, because San Pedro de Macorís, as we have seen, the city, as we have seen earlier, has a concentration of population with respect to the other smaller towns, then we have subdivided the number of schools by 5 different nodes in San Pedro de Macorís, so that each node more or less has an equivalent weight in the network. And these are the different type of bridges, again, and they are quite different, as you can see. Some of the roads are very good, but some other roads are very basic, yes, as we can see. But still, you know, they are critical communications. Sometimes the more basic they are, the more critical they are to actually connect community. In terms of the seismic hazards, there we can see a distribution of shallow and less shallow events in the island. So this is, oops, yes. So this is the area in Haiti where there was the very destructive earthquake. San Pedro de Macorís is here. As you can see, there is quite a lot of activity as well, but very likely most of the events are quite deep, so the effect on the surface is less strong. So the latest analysis in terms of seismic analysis, we can see here. So this is the position of San Pedro de Macorís here. And as you can see, it's pale blue. So in terms of a PGA of 2% in 50 years, which is the typical design limit, we have a PGA of 0.25, which is moderate seismicity with 475 years of return period. But if we go to the extreme event, then that PGA becomes 0.6 in 2,000 years. So we then define the fragility functions for the different building types and for the different bridges type once they are classified. As I mentioned before, we then have the different Bayesian network output. So where we can see that there are quite different percentages between the moderate scenario and the extreme scenario. And we can see that in the extreme scenario, a large proportion of all the municipality will have school in the shutdown condition. And similarly for the bridges, we can see that in the moderate scenarios, most of the bridges will be intact, but some might have, like before, have still a quite high probability of being affected. And in the extreme scenario, of course, that probability of being affected increases substantially. We then want to see the criticality of school municipality for the recovery. So we have two possibilities. We can either rank the municipality by student number, so we might make the decision that we are interested in recovering the towns and the city where there is the largest number of students first. And remember, we have divided these municipalities so that the number of students is not different from one to the other. Or we can, so that will means that, for instance, I will first recover M2, then M10, then M4, and so forth. Or we can rank the municipality by school building damage states. So the probability that I showed you before, we will look at the probability where there is the highest number of damaged schools, and then go to that particular municipality. But remember, because we are doing Monte Carlo simulations, if we are going with this analysis on the school building damage state, for each simulation, that distribution of probability of being in a damaged state might be different. So for each simulation, we might have a different scenario. Yes, so it's more, and we will see the difference in the recovery curves. So then we will go first to the shutdown, then to the partial, then to the intact. Similarly, we need to define a criticality for the bridges. So we can either think that the bridges can be ranked in betweenness and centrality, which is a typical approach for studying graphs. So the betweenness and centrality of an edge in a network is a measure of how often that edge is part of the shortest path between two nodes. So in that case, this would be the ranking, where B6, B5, and B4 are the most critical. B7 and B10 are the next criticality, and then B8 and B9 are the next criticality. Then we have B1, B2, B3, and B11. Or we can rank the bridges following the recovery sequence of the school, which is what I was talking about earlier, i.e. the school, depending on the criticality of the school, then the bridge operator will need and go and recover the particular track that is needed to reach that municipality that we are going to work on. And so this would be, you see, to go from M2 to M10, I will first need to recover B7, then I will need to go from M10 to M4, I will need to recover B10, and so on and so forth. So as a result of this, I have 4 different recovery strategies. One is to recover MC1, one is to use MC1 and BC1, one is to use MC1 and BC2, or MC2 and BC1, or MC2 and BC2, because I've chosen. Or we can use yet a different recovery strategies, which we call dynamic criticality, or also better known as the greedy algorithm, where we rank both infrastructures by maximizing the education recovery at each steps. So, and the education and the maximization is done through the ratio of the number of students in a given municipality divided the time needed to recover that municipality. So, which is the time recovering all the school in the municipality, the time for recovering the bridges that are blocking the way, and the travel time of the 2 operators. So considering all these possible strategies, we can see that we have very different paths. Yes? And as you can see, some of the paths are more detailed than other, because in path 0 and 1, we were considering simply, we were ranking all the school at the beginning, then we were ranking the bridges, and there is no interaction. And the school are ranked by number of students. But in paths 2 and 3, the school are ranked by damage, and therefore, as I said, for each simulation, we will have a different damage distribution, and that's why they look in that way. And finally, for strategy 4, which is the greedy one, we will have initially a steeper level of recovery, as we can see, because we will initially the local optimization corresponds to the global optimization, but then later, as we tend to the end of the recovery, it will slow up a little bit, because basically the greedy path will go first to the easier solution and then later leaves the more complex solution for the latest. So as a result of this different recovery, we see that the best recoveries is strategy 1, where we have the school ranked by number of students and the bridges ranked to serve the school operators. But this is if we just look at the time of recovery. If we look at a typical resilience measure, which is the area underneath the recovery curve, then we find that although the total recovery is a bit delayed, the strategy 4 still maximizes the resilience indicator. And then we can consider the agent-based, we can consider a different way of using the agent-based method, also with reinforcement learning. And this is particular studies that Dr. Sai-Shang Li has recently developed. So in the reinforcement learning, we use an interdisciplinary area of machine learning and optimal control, which is concerned with how an intelligent agent should take action in a dynamic environment in order to maximize a reward signals. So the agent will look for optimal recovery strategy rather than present criticality. And the reward will depend on the Markov decision process. So we have a set of environmental and agent states, SI, a set of action and space, and we will look for the probability of what is the best outcome, i.e. the transition probability at any time t from state S to S prime under a particular action 8. And the immediate rewards is as a result of that transition. And the transition in this case is from the damaged state to the recovery state. So this is what it looks like in terms of the interaction between our agent-based model and the reinforcement learning. I will not go into the details of this. In order to apply the recovery learning here, we are just using the highest probability in the Bayesian network analysis. So this is a deterministic approach, not a probabilistic approach. And we can see that now when we use the reinforcement learning, which is the curve in red, is also doing better than the greedy analysis. And in particular, its recovery time is further reduced with respect to the greedy strategy, and the resilience value is increased. So this one is in the current state, and this one, and we have considered here 4 different let's say 5 different, in fact 6 different recovery strategies using technological and statistical analysis at our best possible way. But we haven't yet considered the retrofitting solution. So these are, if we consider different retrofitting conditions for different for the different building type, and we can go a little bit in detail here, but it's not fundamental. So as we said, there we can put some frame to isolate the infill to avoid the short column and weak story. Here we can also put some steel brace to in reinforced concrete frame that are weak in the longitudinal direction. And for masonry buildings, we can use some buttressing or backstack and some ring beam in order to bring together the diaphragm actions in the building. So we will now have a new set of fragility functions which deliver a better performance towards the earthquake. We can do the same thing for the bridges, so we will have a better performance. If that's the case. And for each of these, you can see that we are also estimating the actual cost with respect to the new building. Yes, so there will be some interventions that will cost more than other. So the first intervention in field isolation is only 5% of the replacement cost, but if we also put steel brace frame, then we go to 30% of the replacement cost of the building, and so on and so forth. Or sometimes the same intervention might actually cost more or less, as you can see, with respect to the different things. And here, similarly for the bridges. So now we also have an economic indicator of how much it will cost us to make the system work better. Okay, oops, I don't know what happened there. So then we can look at the recovery of the school operation with different retrofitting strategy. So we can decide whether, and here we only use the greedy operators, the greedy recovery approach. So we can see whether we retrofit only the school, whether we retrofit only the bridges, or whether we retrofit both. And of course, retrofitting only the school will cost less than retrofitting both. Retrofitting the bridges will cost less, and so on and so forth. I don't know why it keeps doing that. But we can see that we have a reduction of from 206 days to 168 days, so 38 days less in terms of the interruptions, which is a reduction of almost 20% with respect to that conditions. And we can look at, it might not seem much, but basically it's more than a month of lecture less, so it's 7 weeks of lectures. And we can see that the cost per reduced day per student, which is, although retrofitting both costs more, when we divided the total cost by the day that have been gained, we can also see that the cost per student per reduced day, it's actually less if we retrofit also the bridges than if we don't retrofit the school. We retrofit also the school, only the school. One might argue, well, we retrofit only the bridges because it costs very little and it's to the students. But the issue is that retrofitting only the bridges doesn't save the life of the students from the event if they are at school. So it's quite important to consider that. And this metric is very easy because if you think this is less than $10 a day, and very often a student will spend, the family of the student will spend that money to send the student to school in bus fare or in food or in dressing and clothing in order to send the child to school. Yes, so it's very comparable, and therefore it becomes an easy way for also from a policy point of view to discuss investment at a local and more national level. Similarly for the flooding, so the flooding model is much more basic. We only have a susceptibility of flooding for this particular area. I'm almost done. So these are the fragility functions for the floods. We can then look at the flood recovery, and we can see that again, oops, I don't know why there is something that, we can see that after and before the interventions, here actually we can almost halve the number of days lost, so it's quite important. This notwithstanding, we end up, because the number of school affected and the number of students affected is smaller than the total number of students before, then it seems that the cost per student is much greater, i.e. $26 per day. However, we need to think that an earthquake event will only has a return period of 450 years or more, so the probability of occurrence of the earthquake is much smaller than the probability of occurrence of the flood, which in that term will probably occur 10 times, because this one is the probability of, as a probability of occurrence in 100 years, yes? So when we consider the length of time, then this intervention is also very beneficial. So, in conclusions, because I've taken much of your time, the quality of the input information determines the quality of the results, and this is always the problem. How good is the data that we can put in the system? And in our case, we have been working with the Dominican Republic since the World Bank from 2018, so we have a lot of data about the schools, but that's not always possible. The model has several limitations, which I'm now not going to consider, but it's a simplified representation of reality, of course. We have highlighted the numerous uncertainty in the process, and we need to understand that it's not an exact science, but it is sufficient to provide a framework to start thinking in probabilistic terms. And the main objective is to inform the decision-making strategy based on disaster response policy at the local and national level. So, has two benefits. First of all, highlights the vulnerability of the schools, highlights the vulnerability of the bridges, and then it's down to the politician to decide how to use their budget. And what is very important is that they can do this now with data, with some numbers, yes? And with the ability of ranking the different municipalities as we have seen. So the future work is to base implementation for future nationwide application using the reinforcement learning approach, but also using artificial intelligence to try and gather more information. Here there are some more detailed elements for points for reflections, which I'm not going to read through now, but probably they will come up during the discussion, if any. And with this, thank you very much. By protecting students, we are protecting our future, so it's very important. And these are a few indications of things that you might want to read if you want to know more about this. Thank you.